So after coding our recursive solutions for factorial, Fizbits, and Fibonacci exercises, I think we are ready to move to the mother of all recursive puzzles, Tower of Hanoi. The game is simple. We have to move the disks from one peg to a destination peg. We can use one extra peg in order to temporarily move and store disks, but at no time can we have a larger disk on top of a smaller disk. So to better understand how the disks are moved and see the pattern of the moves, let's play one quick game. I'm going to start with only 3 disks. However, no matter how many disks there are, the pattern is the same. So here's the game. Alright, so we have our 3 disks and 3 pegs. In this particular game, the destination peg is number C. So we are moving all the pegs to number C. I mean all the disks, I'm sorry, to peg number C. So the first thing, let's move disk 1 into our one of the pegs, disk 2 into one of the pegs, and let's move this one back on this one. So we moved the 2 disks and cleared the largest disk, and that one is now able to be moved to our destination peg. So I'll move it there, and that concludes one batch of the moves. Now we're going to do the second batch. So in order to move disk 2 to the destination peg, we need to clear it, move the smaller one away, and this one can now go to our destination. And finally, since we only have 3 disks, the last one can go straight to our destination on top. And we won with 7 moves. So you could see that to simulate a pattern with recursion, we simply need to know the number of disks that are available. In this case, we started with 3 disks. And also which peg is our source peg, and which one is the spare peg, and which one is the destination peg, which in this case was the peg number 3. So once we know these, we can simulate the moves by changing the peg's destination. For example, as you saw, after the first batch of disks moved, the remaining disks were on peg number 2. That was originally our spare peg, but now, after the first batch of moves, it became our source peg. In other words, that's the peg from which we will be moving the disks away. And the peg number 1, which was originally the source peg, will now be the spare peg because it's empty, and now we will temporarily move some of the disks in it. So in order to simulate the 2 batches of moves, we will call the recursion twice from within the recursive function. And of course, in both cases, we need to know when to stop the recursion, and in both cases, that's when the largest disk is the last disk available for the move. So let's see how it looks in code. First, let's call the recursive function. This function will not return any value, but instead we will display on the screen how the moves are being made. So this is how it's gonna look. So if we move from disk 1 to disk 2, this will be the notation, or if we want to move from disk 3 to disk 1, it will be this notation. Basically, the source disk will be the first number, then the arrow, and then the destination disk to which we moved it to. Okay, so as I mentioned previously, we need to supply the number of disks, the source peg, destination peg, and spare peg as arguments into our function. So the whole function signature will be something like this. I'm going to code a static void, and I'll just call it tower. And like I said, the first argument will be the number of disks, so it's gonna be an integer n. The second will be the number of the peg that is the source peg, so it's gonna be an integer again, and I'll call it source peg. Then it's the destination peg, so again it's an integer, and finally the spare peg number. So in our case, we can make the destination peg either the middle one, number 2, or 3, which is how the game was in the one that I played online. So let's just do both, but first we'll do number 2 as first, and then we'll make destination peg number 3. Anyway, the next we need to code the condition when the recursion stops. Again, as I mentioned before, it is when the last disk, which is the largest disk of the badge, of the move badge, is left. So this is how it's gonna look. We'll do simply if statement, and if the number of disks that is available to move is 1, then we can now display the move itself. So like I said before, the move is going to be displayed as source peg, arrow, and then destination peg. And we can place the source peg with the combination with the arrow and add the destination peg. So we'll simply move the latest or the last disk to the destination peg. Now, because of the rule that the disk has to be smaller on top of the larger disk, we know that once only one disk is left, then that is the largest disk of all the moves available to us. Now, if this condition is false, we'll do an else statement. We have our condition that stops the recursion. Now, in our else statement, like I mentioned before, we will call the function recursively twice. And both the moves will decrease the number of disks by 1 because we are moving one disk at a time. However, the designation of the pegs will be different. Remember from the demonstration that we start with the peg 1 as source peg, but after the first batch of moves, all the disks were on the peg number 2. So that will be our source peg now. So in the first call to the function, I'll simply call the tower, and I will pass the n minus 1, like I said, decreasing the number of disks by 1 because we are moving one disk at a time. Now, the source peg remains the same for this particular move, and in the next one we will switch them. So the source peg is the same as it was. However, what changes is the destination peg and spare peg. They are switched now. So our third argument, which is the destination peg, will be now the spare peg, and vice versa, the spare peg is now becoming the destination peg. So that's our first call. So now we also have to display, of course, the move itself like we did here. So I'm gonna copy it, and we are displaying it after this one move. And now the second call to the function, so we will use the tower again, and once again we will do n minus 1. We are using one disk at a time, but now the first peg is going to be our spare peg, our second peg is our destination peg, and finally our last peg is the source peg. That's where we are moving the disks from. Okay, so this is the recursive function, and all that is left to code is the main method. So the first thing, we need to know how many disks that are going to be used. So I'm going to create a variable, call it disks, and I'll initialize it to 0. And I will ask the user to input the number of disks, and then I will store that number in our disks variable. However, since the disks is integer and the input will be string, I have to convert it to an integer. So we ask for the number of disks, and we will store that value in our disks variable. And now we are ready to call the function itself. So we will call tower, and we will pass the number of disks. The next argument is the source peg. So initially it's the peg number 1. Then it's the destination peg, where we want to move all the disks, which is the peg number 2. And finally, peg number 3 is our spare peg. Alright, so let's run it and see what we get. So here's the screen. I'm going to enter 3 disks to begin with. And you can see here's the moves. First, I will move the disk from peg 1 to peg 2, then from peg 1 to peg 3, and so forth. In fact, let me run the game again, and I'm going to follow these moves and see if it works. So it's 3 disks. So the first says from peg 1 to peg 2. So I'm going to grab one and put it here. Then from peg 1 to peg 3, that's correct. Then from 2 to 3, and from 1 to 2. And then from 3 to 1, from 3 to 1, and from 3 to 2, and finally from 1 to 2. So you can see that we get the correct moves. Again, for this particular version of game, they assume that peg number C is the destination peg. That's why it still actually goes as if the game is not finished. But we can simulate it now too. To do that, all we have to do is switch the way we are passing the arguments. So now, instead of number 2 being our destination peg, it's going to be the number 3. And our spare peg will be number 2. Now one more thing we can add is a counter. Basically it will count how many moves we make. So I'm going to declare a counter variable, but since we want to keep the value of the counter and just keep adding to it after each move, I'm going to declare it on a class level. So up here I'm going to create a variable of integer, call it counter, and initialize it to 0. And now, after each time we write the move, I'll simply increase the counter by 1. So I will do counter plus plus. It's telling me that it needs to be static because we are not using any classes. So I will call static integer counter. And also I will increase it down here after we display this move as well. So our counter plus plus. So now all I have to do is add the counter into our output. So before the source peg I will do counter plus maybe an empty space, and then I will display the move itself, and I'll do the same over here. So let's run it again, but this time let's do 4 disks and we can test it again in our game. And you can see that it took 14 steps, actually 15 because we start from 0. The first number is the counter. And let me just follow the steps and see if we get the same result as the game. So I'm going to start a new game, and this time I will have 4 disks, and the first one is moved to number 2. Remember, disk C is our destination now. Another move is 1 to 3, from 2 to 3, from 1 to 2, from 3 to 1, then from 3 to 2, then from 1 to 2, 1 to 3, that's our largest, it's in the destination now, then from 2 to 3, 2 to 1, 3 to 1, and now we have the second largest going to C, which is the peg number 3, and finally the batch is 1 to 2, 1 to 3, and 2 to 3. And you can see that we won with the least number of moves possible, so our program works correctly. Alright, so well, I hope this video was helpful, and I hope that you can now better understand how recursion works and also how to use it. Thanks for watching, and keep on coding.